Hello, welcome. In the next few minutes, we are going to discuss a formula that is quite useful for determining the angle between two vectors. And this is a way of connecting inner products with a very well-known function from trigonometry, which is the cosine function. So one visual representation of this is here, in which there is a vector v and then there is a vector u, and we think about the angle between these two vectors, which here is called theta. So in this visual representation here, theta is an angle between 0 and 180 degrees, or between 0 and pi radians. But in general, we're interested with vectors that have complex entries. But the same notion applies. So the formula that connects the inner product with the cosine of theta, the cosine of the angle between these two vectors, is the formula that we display here. And it is important to note that this formula involves the inner product between u and v, but we're involving in general the real part of that inner product. Okay, and the real part of the inner product between u and v then is equal to the norm of u times the norm of v times the cosine of the angle in between. An important feature here is that this allows us to come up with an approximation for the angle. So once we have knowledge of u, v, the norm of u, the norm of v, and then basically we could say, okay, from this formula we have something that looks like the real part of the inner product between u and v. Okay, and if we solve for cosine, then we would be dividing here by the norm of u, and then the denominator also involves the norm of u multiplying the norm of v. Well, this fraction, this whole ratio now, would be exactly equal to cosine of theta, right? If we solve for theta. So we have cosine of theta equals to that expression, and if we take the arc cosine, or the cosine inverse function, in both sides of that expression, then that leads to this expression. Okay, so you could, some of you may be familiar with the inverse cosine. Some of you may write this as actually arc cosine. Okay, arc cosine. That's another trigonometric function, and is used to compute the exact values of angles. One thing to note is that whenever the inner product is 0, okay, if the inner product of two vectors is 0, that would mean that the two vectors are orthogonal, and that would make this right side of the equation to be 0. We would be taking the cosine inverse of 0, and automatically from that we get that that angle is 90 degrees, or pi divided by 2, pi halves. So let's work out an example. We first work an example in which the imaginary parts of each entry in both of these vectors, the imaginary part is 0 on every entry, and so this makes the calculations a little easier. So we first compute the inner product between u and v, and here, since the imaginary parts are 0, thinking conjugates, it's rather straightforward. And importantly, then we find that the inner product here equals 15, but this is really 15 plus 0i, right? So here we would find that the real part of the inner product between u and v. So what we find is that in this case the inner product has 0 imaginary part. In other words, the real part of the inner product is the real part of 15, which is the number 15. Also, so we write that there. So the norm of the vector u, in this case is 3 times square root of 3, and the norm of vector v is square root of 17. So we can use this information in both sides of the equation. So basically in that equation that involves, that formula involves the inner product and the cosine of the angle, we would replace inner product with 15. We have a number for the norm of u, another number for the norm of v, and the only thing that would be unknown is cosine of theta, and specifically theta, right? So this leads to the following expression. And from this expression, cosine of theta equals to that number, we could solve for theta, right? This is the part where we could take the cosine inverse in both sides of this expression, cosine inverse in both sides. So solving for theta here becomes the arc cosine or cosine inverse of the number 15 divided by, and this is a long denominator there, you can write 3 times square root of, this would be square root of 3 square times 17, right? So, excuse me, square root of 3 times 17. And this would give an expression for a real number, and that would be the value of that cosine in radians. If you would like to know what that value is in degrees, then you have to do a conversion, a little bit of a conversion. So let's now consider two vectors that have some imaginary parts that are not equal to 0. So for example, we may have the vector 3i, 3, 0, and let's consider another vector whose first entry is simple but not quite the same as we did before. So let's say this entry is 1 plus I. Okay, second entry is going to be 0, and the next entry is going to be 4. So we're going to consider this to be the vector u, and this to be the vector v. And now we're going to do the following. We're going to compute the inner product between u and v. Okay, remember this is a Hermitian inner product, and so that means that this calculation is going to involve, we have products, it's going to be a sum, it's going to have 3 terms, okay, and this is something that will look a little bit like this. So the entries of the first vector, we are going to compute the conjugate of those entries. So the conjugate of 3i is minus 3i, and the conjugate of 3 is 3, that has a 0 imaginary part, and the conjugate of 0 is 0. Okay, that was easy. And now we're multiplying by these entries, so minus 3i is multiplying 1 plus I, and then 3 is multiplying 0, and then 0 is multiplying 4. So this is convenient because there are some terms here in this sum that become 0. We're left with minus 3i minus 3i squared, and we can simplify that I squared is going to be -1, so this is equal to minus 3i minus 3 times -1, and that gives us positive 3. So remember, what we really care is about the real part of this inner product. So what we're finding is that that real part is going to be the number 3. So what we just found is that the inner product is 3 minus 3i, but the real part of the inner product is simply the number 3. So now what we can do is to write the formula that we know, right? So we are going to write that we're interested in writing the real part of the inner product, which in this case is 3, equals the norm of the vector u times the norm of the vector v times the cosine of the angle between these two vectors. And the only thing that's left here is to compute the norm of the vector u. So it so happens that in this case, the norm of the vector u is going to be square root of 18, and then the norm of vector v, you have to do this computation on the side, this is going to be square root of 18 also. Okay, and so the only thing that's unknown in this expression is cosine of theta, but you can very simply solve here for cosine of theta. So you'll find that cosine of theta, I'm going to write cosine of theta on the left. This would be 3 divided by square root, and I just write 1 square root of 18 times 18. That would be 18 squared, and so this gives you 3 over 18. Okay, and we find this number, and we can easily use the cosine inverse function to solve here for theta. And this is how you apply the formula that involves inner product between two vectors with complex entries and the angle between those vectors. Thank you.